Okay, hi guys. So I want to give you a deeper understanding of what a depth first search is. So a depth first search, if you start from the point A, this point, and it reaches at this point, if it decides to go with B first, it's going to explore every single thing it sees under B before it comes back up to this point and then explores everything it sees under C. So basically, depth first search goes as deep as possible in the node that it finds before coming back up to check the depth of another level. So let me just solve that out. So let's start with iteration one. And the key thing you should notice is that depth first search uses what we call a stack data structure, which means basically it's like plates. You can stack plates on top of each other, but you can't collect the plates from the bottom. You have to collect the plates from the top, lest the entire thing breaks down. So that's what it uses. It uses a last in is the first out. Basically, whoever was the last person to put their dinner dish is actually the first plate you end up washing. So, for iteration one, we visited, but in this case, we're going to write something. We're going to write stack, not queue. So, the first person visited is A. Iteration two, we're going to say A has not been visited. A was put in the stack initially and has visited. Now, the next people who will enter the stack is actually the neighbors of A, who are B and C. But we're not going to write it as B, C. No, we're going to write it as C, B. Why? Because depth first search is last in, first out. If we're going to go for iteration 3, who's the last in this case? B. So it's the one that will be called the first out. And C will remain. Now, you have to add in the neighbors of B. The neighbors of B are D and E. I believe you can see it in this case. You're not going to write DE, you're going to write E, D, because it's D you want to explore first. So it's not going to be iteration 4, sorry. The visited will be, who's the last in? D. The visited will be D and mean C and E. Does D have neighbors? You always look at when you visit a node, you have to look at its neighbors. If it has neighbors, you add those neighbors to the stack. In this case, yes, D has neighbors. It has neighbors H and I. You can see it here. We're going to write it as I and H because we're going to explore H first. So iteration 5 is simply going to be the visited will be A, B, D, and who? H, leaving you with C, E, and I. Iteration 6. Does H have any neighbors? H has no neighbors, so we're free. DH simply just visits I. This is I, sorry, not C. Only C and E. Then iteration 7. Sorry, let me write it down here. Iteration 7 is going to be A, B, D, H, I, E. Now, does E have any neighbors? Sorry, not E. E. Now, does E have any neighbors? Yes, E does. E has two neighbors, J and K. We're going to add J and K to the mix. The C is already there. We're simply going to add J and K. We'll add it as K, J because we want to explore J first. So this is the stack. Iteration 8. Going to be the first will now be A, B, D, H, T, E, J. Does J have a neighbor? No, so we carry on. What's normal? It will be S. I9 as iteration 9. A, B, D, H, T, E, J. You're going to add K to the Q. Now C is remaining. Now next you're going to now visit Q, C. Now you notice how we went down and search everything under B before we're now coming back to C. And then we're going to search everything under C. So when you add C to the Q, A, B, D, H, T, E, J, K, C. Does C have any neighbors? Yes, C has two neighbors, namely F and G. So you're going to add F and G, but you also want to explore F first. Last in first, I remember. And so you search F, then you check who are the neighbors of F, and it goes so on and so on. I believe this will actually use 16 iterations before you're done, but it's basically the same thing repeated over and over again. So any questions you have, do not hesitate to ask in the comment section. Thank you for listening.